Welcome everyone to another semester of the Lab Safety Lecture for the Electrical and Computer Engineering Department for the University of Nevada, Las Vegas. Today we will be covering topics that you need to know to stay safe while working in the lab or in the field when dealing with voltage and current. In the lab we have 12 safety rules that must be followed, and these rules are as follows. Number 1 rule: safety takes priority over all experiments and lectures in the lab. This is the most important rule. Never do anything that you feel is unsafe. Rule 2: no food or drinks are allowed in the lab. We only allow bottled water in the labs. Bottled water has a minimal number of electrolytes that allows current to pass through liquids and foods. Of note, when skin becomes moist or wet, the ability for it to protect you can drop by an order of magnitude. Rule 3: if you are going to be using a power supply in any experiment, 2 people are required to be present in the lab. A power supply is the piece of equipment found in the lab that is the most able to cause damage to the user. If you cannot find a second person to be in the lab when using a power supply, it is required that you do not use the power supply. It is better that the lab be late with an explanation than you to be injured by using a power supply alone. Rule 4: no crossing wires from desk to desk. The explanation for this is given that the power supplies or devices, when connected in series or parallel, can cause a situation where an accident can be more likely to happen. Rule 5: cell phones are permitted, but step away from the bench when using them. The reason that we ask you to step away from the desk and go outside to talk is that you talking on the cell phone is a distraction to other people around you and may lead to accidents. Rule 6: when in the lab, both sets of lights must be on. Rule 7: every hour we recommend you take a 10-minute break. These 10-minute casual breaks allows for the student to step away from a problem that they may be having and they can see no solution to, for the labs all do work. Rule 8: check and double check that all your equipment is turned off when leaving the lab. This allows for the station to be safe for the next person that wishes to use it. Plus, by having the equipment turned off, you're saving power and thereby making the power consumption of the world a little less. Rule 9: computers at the lab station are for academic work only. Recently, we've had students using the computers to watch YouTube or to watch other people play video games or play video games themselves. If you wish to do that, please go down to the TBE A311 lab or any other lab here on campus that's not in the Electrical and Computer Engineering Department. Rule 10: only trained engineering students that pass the safety exam are allowed in the lab. If you wish to bring other people into the lab, please see the lab director or the lab manager so we can schedule a tour. We wish to keep everyone safe when visiting the lab. Again, only people that have passed the safety exam are allowed in the lab. Rule 11: do not use any equipment that is not working properly or known to be broken. Report missing or broken equipment immediately to the lab director or the lab manager. Never let anybody pressure you into working on equipment that you know to be broken or that you are not familiar with. If this happens, please come and see the lab director or the lab manager immediately. Rule 12: no student is allowed to use any equipment they are not trained on or not familiar with, especially soldering stations, since they are the #1 injury causer here in the B350, B311 labs. Soldering stations are hot enough to melt metal, so do not test them with your fingers. There are other ways of testing to make sure that the soldering tip is hot. The safety lecture is important because when students enter the lab, they are more concerned about what they need to get done so they can complete the lab than safety. When you enter the lab, instead of worrying about what needs to be completed, you first need to think about what you need to do if there is an accident, how you will handle the situation, including a game plan for how to escape or how to handle somebody that has been injured. When you enter the lab, you assume that everything will work perfectly the first time. No one worries about what happens if things do not work perfectly and what happens if they are distracted and there is an unsafe situation. This is why the safety lecture is the most important part of any lab. People must be educated on general safety concepts and safety issues that arise from dealing with electricity. You were not born with the innate knowledge of how to deal with electricity safely. As part of the safety lecture, we wish to take a more direct approach and avoid accidents. Therefore, we need to educate you before any accident or incident occurs. In the past, lab directors and lab managers have passively droned on and on about the importance of safety and letting the students know the importance of safety. This system needs to change. We need to educate students with a deeper technical knowledge of prevention and treatment when injuries happen due to electricity in the labs, other than traditional don't kill yourself approach. Accidents will happen. It's just a matter of time. Knowing how to keep a calm head, provide immediate treatment, and follow up with professional medical care makes a difference between a minor and major injury. How are we making things different? First, do not ever allow any student, professor, or any other person pressure you into doing something that is unsafe. If you have the smallest doubt on the safety of what you're doing, back away and immediately approach your TA, the lab manager, or lab director. Do not be afraid to come forward. If you have a concern about safety, there are probably 10 other people with the same concern. It is easier to answer it once while everybody's paying attention than answering it 10 separate times. If you witness someone doing something unsafe or dangerous, immediately contact your TA or the lab director or the lab manager to inform them. All safety reports will remain anonymous. If you willingly or directly violate safety concerns, you may be subject to receiving a 0 for that day's lab and possibly failure from the course depending on the severity. The laboratory has installed a kill switch, a big red button found at the back of the lab near the door that you entered, near the light switches, near the circuit breaker panel box. If you suspect someone is being electrocuted or is in imminent danger of being electrocuted, immediately press the big red button and it will shut off all electricity to the lab except the lights. Every laboratory has a fire extinguisher in it. It is located near the entrance of every lab. If there is a fire or sparks, please use the extinguisher by aiming the black cone at the fire and emptying the contents of the extinguisher. Again, it is difficult to determine when a fire has been put out, so we recommend that you empty the contents of the extinguisher. These cannot be reused, so once you have started using it, please empty it. It won't be refilled. It'll be emptied even if it is partially still filled and then refilled and tested. Every fire extinguisher has a card attached to it. This card tells you when the fire extinguisher was last inspected, when it is due to be inspected again, who performed the inspection, a 24-hour emergency telephone number. If this card is missing, please let your lab director or lab manager or TA know immediately. If there is an emergency, the number is 702-895-3668. If there is a fire, the way to use the fire extinguisher is hold it upright, pull the safety pin, aim the horn at the fire, hold down the handle to release the gas, and direct the discharge at the base of the flame. Again, use the complete contents of the bottle. It will not be reused. It will be emptied and refilled and checked. Fire extinguisher classification. Knowing what type of fire you are facing and what type of extinguisher you have makes a difference between a successful extinguishing of the fire or not. A Class A type fire extinguisher is for the ordinary combustible materials such as paper, cardboard, and plastics. Class B involves flammable or combustible liquids such as gasoline, kerosene, grease, or oil. Class C involves electrical equipment such as appliances, wiring, circuit breakers, or outlets. Never use water to extinguish a Class C fire. The risk of electrical shock is too great. Class C extinguishers do not have a numerical rating. The Class C classification means the extinguisher agent is non-conductive. Class D fire extinguishers are for commonly found chemical lab. They are for fires that involve combustible metals such as magnesium and so forth. Common types of fire extinguishers. APW, air pressurized water, suitable for Class A fires only. Dry chemical, come in a variety of types, but are suitable for Class A, Class B, and Class C fires. These are filled with a foam or powder and pressurized with nitrogen. Dry chemical extinguishers have an advantage over CO2 extinguishers since they leave a non-flammable substance on the extinguished material, reducing the likelihood of reignition. Carbon dioxide extinguishers are used for Class B and Class C fires. This type of extinguisher is what is found in the B311, B348, B350, B309, and B313 labs. A CO2 extinguisher contains carbon dioxide, a non-flammable gas that is highly pressurized. The pressure is so great that it is not uncommon for bits of dry ice to shoot out of the nozzle. CO2 extinguishers do not work well with Class A fires because they may not be able to displace enough oxygen to put out the fire, causing the fire to reignite. CO2 extinguishers have an advantage over dry chemical since they do not leave a harmful residue. This makes a good choice for electrical fires on computer or other favorite electrical devices. It is vital to know what type of extinguisher you're using. Using the wrong type of extinguisher for the wrong type of fire can be life-threatening. Even though dry chemical extinguishers would be better for this lab, we use carbon dioxide because we do not wish, if there is a fire, to damage more than the equipment that is currently having the issue. A dry chemical would damage all equipment in the local area and possibly other stations. Therefore, we use a CO2 extinguisher in these labs. Laboratory emergency numbers. From any on-campus telephone, you can pick up and dial 911 and it will contact the UNLV police. From a cell phone, if you wish to contact the UNLV police, you will need to dial 702-895-3668 extension 2. More laboratory emergency numbers. 911 is 911. Campus police 53668, again from any on-campus phone. Las Vegas Metro Police Department is 702-795-3111. Ambulance dispatch 702-384-3400. If you wish to contact the campus operator from any campus phone, press 00. The department phone number, which everyone should know, is 702-895-4183. If there is a chemical or radioactive material discharge, Monday through Friday, you can pick up any campus phone and dial 702-895-4226 or, since it is a campus phone, 54226. If there is a accident after hours, you can dial 702-895-3668 or from an on-campus phone 53668. And if you wish to talk to the Office of Public Affairs from a campus phone, you can dial 53102 or from a non-campus phone 702-895-3102. Every laboratory has a first aid kit. The first aid kit is located near the door in all laboratories. First aid kits are useful for minor injuries and temporary solutions for major injuries. You do not need to ask permission to use the first aid kit. We just ask that if you use the first aid kit, that you please notify the lab director, the lab manager, or the TA so we can refill the first aid kit. First aid kits. In the picture to the right is the contents of the first aid kit. Knowing what's in the kit makes the kit useful. Please familiarize yourself with what's in the kit. Located in the first aid kit is bandages of various sizes. These are useful for small cuts and burns that may occur in the lab or anywhere on campus. Alcohol prep pads are found inside the first aid kit and are typically used for cleaning the skin around in an area that needs an injection. For wounds bigger than a typical band-aid can cover, there are large bandages found in the first aid kit. Keep in mind, skin should be disinfected before applying a bandage. Located in the first aid kit is a reusable hot and cold pack. This can be useful in localized swelling, bad headaches, strains, and sprains, and very useful for numbing an area, maybe even after a long, brutal test. An instant cold pack is also in the first aid kit and is similar to the reusable hot and cold pack but is chemically activated. This pack immediately gets cold and is fantastic for pain relief. In the first aid kit is an assortment of sealed medications. In this kit are non-aspirin pain relief and antacids. Be sure the packages are sealed before using them. Again, great for after a long stressful day of electrical or computer engineering. There is a collection of rubber gloves found in the first aid kit. Rubber gloves should be used when blood is present. If a wound is exposed and bleeding, the person providing medical care should wear the gloves to prevent spreading of any illness. Iodine prep pads are also found in the first aid kit and are useful to prevent infection of all types of cuts and abrasions. They should be applied to any cut or abrasion before a bandage is applied. Unwelcome insects sometimes cause injuries in the lab. Insect relief pads are found in the first aid kit and can be used for insects' bites and stings. Due to the presence of venomous spiders in Las Vegas, it is wise to obtain a sample of the insect that bit you if you are not familiar with it. The most famous venomous insect in the Las Vegas area is the black widow spider, the telltale sign of which is the red hourglass shape on the abdomen. Black widow spiders are not normally found in the lab. They are usually from people bringing in equipment from home. If you happen to see one of these in the lab, please inform the TA, the lab director, or lab manager immediately so that professional insect removal people can be called and the situation can be remedied before any accidents occur. The brown recluse or violin spider would rather run than attack, but when backed into a corner is even more dangerous than the black widow. The bite from a brown recluse causes incredible pain to the bite area due to the total destruction of tissue. This type of bite causes necrosis, which is the complete destruction of cells, including regrowth centers. The damage due to necrosis usually must be removed surgically. If you happen to see a brown recluse spider, again, immediately back away and contact the lab director, the lab manager, or your TA. We will call professional exterminators to remove these spiders. A CPR face shield is included, which is sterilized with alcohol. CPR must only be performed by those trained in CPR. More assorted bandages and eye pads are included in the first aid kit, as shown to the picture on the right. The laboratory first aid kit also includes scissors and tweezers. Tweezers are good for removing foreign objects embedded inside your skin, like those nasty bits of wire that students seem to always jam into their fingers or arms. For serious wounds, the first aid kit should be used as a temporary solution until you're able to seek professional medical help. A large cut or burn, for example, can be disinfected, wrapped to protect the wound area, and then you must seek professional medical attention. Whenever you use the first aid kit, again, notify the lab director, the lab manager, so that we can restock and assess the situation. Sometimes there are serious injuries, but people decline medical help because they have a test later that day. Health is the most important thing always. We can always work with your professors to explain what happened and why you may need to make up an assignment or test. Again, safety and health is the most important. The rest of it is secondary. No one in the department is a medical expert. We try to be trained so that we can provide quick, safe help immediately after an accident, but one should always seek proper medical care after an injury. There may be long-term effects that only trained medical nurses and doctors are aware of. You will never get in trouble for reporting an injury to the lab director, lab manager, or TA. Accidents will happen and need to be treated seriously regardless of the severity of them. After an injury, All we care about is trying to figure out why it happens so it can be prevented in the future. Emergency exits and meeting spots, where they are for each lab. For B350 and B348, you will immediately proceed out the doors and turn left and go down the fire escape and meet in the parking lot. For the B311, B309, and B313 labs, you will immediately exit the doors, turn right, head through the fire doors to the balcony, turn right on the balcony, immediately proceed to the emergency staircase, go down the staircase, and again meet in the parking lot. If you suspect a fire or problem, immediately inform the TA, lab manager, or lab director, and then calmly leave the lab and proceed to the emergency meeting spots. Hazards of electricity. There are three types of hazards when dealing with electricity: electric shock, electric arc, and electric blast. It is important as an engineer to understand the risks and dangers of working with electricity. Just because you are working in a low voltage laboratory setting does not mean serious injuries cannot occur. Definitions. Electric shock. The physical simulation that occurs when electric current flows through the human body. The distribution of current flow through the body is a function of the resistance of the path through which the current flows. Symptoms of shock is mild tingling sensation, violent muscle contractions, heart arrhythmia, and tissue damage. Again, if somebody is being shocked, do not try to run over and touch them or grab them or help them while they are being shocked. Proceed to the big red button found at the back of every lab. Depress that. That will cut the electricity off that is causing the damage to the person, at which point you will be able to render assistance. Physical condition of the individual greatly influences the effects of current flow. A given amount of current flow will usually cause less trauma to a person in good physical condition. If the victim of shock has any medical problems, such as heart or lung ailments, these parts of the body will be severely affected by relatively low currents. Influencing factors. Current duration. The amount of energy delivered to the human body is directly proportional to the length of time the current flows. From the equation below, it can be seen that the energy delivered to the human body is proportional to the current squared passing through the body, the resistance of the body, and the time that the current flows. A way of visually representing this is when you cook food. It's the heat of the cooking device and the amount of time that you are cooking. Again, heat relates to the amount of power, current squared times resistance, and the time that you are cooking. When dealing with electricity in the lab, please be responsible. Again, you do not wish to be the cooked food. Electrocution. Having externally sourced current flowing through the human body. And it will tend to flow through the current paths used by the human body's central nervous system. Since the external current will be much larger than the normal current flow of the human body, damage can occur to the nervous system. Damage to the nervous system can be fatal even with relatively short durations of current. Generally, a longer duration of current through the heart is more likely to cause ventricular fibrillation. Fibrillation occurs when the externally applied electric field overlaps with the body's natural cardiac cycle. Rapid and inefficient contractions of muscle fibers of the heart cause disruptive or nerve impulses. Important frequencies. Knowing what frequency you're dealing with can determine what the harmful effects are. DC, or 0 Hz to 10 kHz, is a low frequency, usually found in commercial electrical power. Its harmful effects are joule heating, which means basically energy to the cell, and destructive cell membrane potentials. Another frequency that you may encounter in a lab is 100 kHz to 100 MHz, which is radio frequency. This also is joule heating, but also dielectric heating of the proteins, which basically means the proteins are vibrating in a violent manner. 100 MHz to 100 GHz microwave, again dielectric heating of water, and infrared, visible light, and ionizing radiation will not be found in any of the labs here, but their harmful effects are shown. AC and DC. Differences of applied voltages to the human body are apparent even between DC, 0 Hz, and standard power line frequency, 60 Hz. When equal current magnitudes are compared, 0 versus 60 Hz, DC versus AC, DC seems to exhibit two differences. Victims of DC shock have indicated they feel greater heating from the DC. And 2, the threshold for what a person can let go tends to be higher with DC. Influencing factors, magnitude. Higher voltages can be more lethal for several reasons, but most notably, for voltages above 400 volts, the electrical pressure may be sufficient to puncture the epidermis, the skin. Since the epidermis, the outer layer of skin, is the only significant resistance to current flow through the human body, the current flow will increase dramatically when the epidermis is punctured. The higher the voltage, the more likely to cause unpredictable arcing. Power supplies connected in series with wires strung from desk to desk can achieve a voltage of 400 volts or greater. Therefore, no crossing from wires from desk to desk. Influencing factors, the most important slide to dictate how to stay safe when dealing with electricity. As you can see from the table, a finger touch can vary anywhere from 40,000 ohms to 1 million ohms dry, but the same finger wet can vary from 4,000 ohms to 15,000 ohms. Once the human body is punctured, you can see that the human body internal resistance can drop as low as 200 ohms to 1,000 ohms. A drastic resistance decreases once the surface becomes wet and once the human body is punctured. Knowing the conditions of the body and the voltages you're working with can mean major differences between injury and safety. Knowing working with small voltages and dry hands can lead to no injury. Working with large voltages and dry hands can lead to major injuries. And working with small voltages and wet or inside the human body can lead to major injuries. Knowing the situation and the resistance of what you're dealing with can be the difference between no injury, minor injury, and major injury. If you are working in a situation where you possibly may be shocked or electrocuted, or are afraid of being shocked or electrocuted, personal protective equipment made of rubber is a great insulator. It is not big and bulky and can virtually ensure that nothing bad will happen if you are careful to cover your hands and feet with rubber shoes and gloves. Another important slide to dictate how the human yourself will respond to current magnitudes is presented in table 1.4. Below 1 milliamp of current passing through the human body from an external source is imperceivable. 1 milliamp is where the human body operates by the brain passing electrical currents to the appropriate muscles. 1 milliamp provides a mild sensation, tingling. 1 to 3 to 10 milliamps is a painful sensation, whereas 10 milliamps is right on the threshold of paralysis. Electrical hold. Electrical hold is where you cannot release your grip or move your arm to prevent contact from the external current source that is now passing current through the body. At 30 milliamps from an external current source, you will be on the threshold of respiratory paralysis. At 75 milliamps, you will be on the threshold of ventricular fibrillation. At 250 milliamps, you will be at the 99.5% threshold of ventricular fibrillation. At 4 amps, heart paralysis. Your heart stops beating. And at greater than 5 amps, your tissue starts burning. When dealing with electricity, it is most imperative that you know the voltage that you are dealing with and how much resistance will be present in your body that will be exposed to the voltage. This will dictate how much current will pass from the external source through your body. The external electricity or current will follow Ohm's law. Voltage equals current times resistance. Therefore, the current through the human body will be given by the voltage that you're dealing with and the resistive path that you are presenting to the voltage source, or voltage divided by the resistance. Current flow of approximately 20 milliamps is sufficient to cause a person to be in a state of electrical hold. Again, the threshold is 10 milliamps, so 20 milliamps is twice the threshold. Electrical hold is a condition where the muscles are contracted by the passage of electrical current from an external source, and the individual is unable to overcome this response. Again, your brain sends 1 milliamp signals. 20 milliamps will be 20 times greater than what your brain can send. Like any injury, certain parts of the body respond very poorly to the flow of external electricity at much lower thresholds than other parts. Electrical arcs, ANSI standard 100 or IEEE standard 1988 defines electrical arc as a discharge of electricity through a gas, normally characterized by a voltage drop in the immediate vicinity of the cathode approximately equal to the ionization potential of the gas, which basically means that the electric field has exceeded the dielectric strength of the gas. Therefore, the gas breaks down and current now has a path to flow from one side of the voltage to the other. Arcs can occur from several scenarios. When the voltage between 2 points exceeds the dielectric strength of a gas, when gas becomes superheated with the passage of current through a conductor, when two contacts part while carrying a very high current, the last point of contact is superheated and the arc is created due to the inductive flywheel effect. Shown in Table 1.5 are the ignition temperatures and characteristics of clothing fibers. What do you think is the best choice to wear in the lab? What is the worst choice? Why? The most important of all arc energy equations is the one that determines the energy transfer from the arc to the nearby body, U. This is called the incident energy. This information can be used to determine the necessary level of protective clothing required and can be used in the performance of risk analysis. The Lee method shown below was developed by Ralph Lee and predicted the heat energy received by an object. Can be calculated using the equation. Arc burns. First-degree burns. Painful trauma to the outer layers of the skin. Little permanent damage results from a first-degree burn because all the growth areas survive. Healing is usually prompt and leaves no scarring. Second-degree burns. Results in relatively severe tissue damage and blistering. If the burn is to the skin, the entire outer layer will be destroyed. Healing occurs from the sweat glands. Third-degree burns. A complete destruction of the growth centers. If the burn is small, healing may occur from the edges of the damaged area. Extensive third-degree burns usually require skin grafts, and hopefully none of you have ever experienced third-degree burns. Electrical blast. When an electric arc occurs, it superheats the air instantaneously. This causes a rapid expansion of air with a wavefront that can reach pressures of 100 to 200 pounds per square foot. Skin is the outer layer that completely encloses the human body. Each person's skin weighs approximately 4 pounds and protects us against bacterial infection, physical injury of underlying cells, and prevents water loss. The main regions of importance for electrical purposes are the epidermis, the sweat glands, and the blood vessels. The epidermis, the top layer of the skin, that is 0.1 to 1.5 millimeters thick, which means 4 thousandths to 60 thousandths of an inch thick, mils, and is made up of 5 layers with the outermost layer called the stratum corneum or horny layer. The horny layer is comprised of 10 to 30 layers of dead cells, which are devoid of water, which have been pushed to the surface from the lower layers of the normal growth process. It is called the horny layer because the cells are toughened like animal horns. The horny layer is composed primarily of a protein called keratin. Of all the skin layers, keratin exhibits the highest resistance to the flow of electricity. As the horny layer becomes toughened by repeated physical exertion, calluses form and the skin becomes even more resistant to the flow of electricity. This layer is far the greatest protection against serious electrical damage. We have high kiloohms to megaohms. If this layer is compromised or removed, the body's internal resistance to electricity is almost none, typically 200 ohms. It is not recommended that you attend lab with wet hands, or hands that have been moisturized before lab. Again, it is the horny layer, the dead skin cell layer that lacks moisture, that provides the greatest protection against electrocution in the lab. If you are worried about being electrocuted in the lab, it is recommended that you purchase rubber gloves, which will provide a great resistance to external current flow to your hands. Electrical burns usually come from at least 4 different sources. Number 1, physical contact with conductors, tools, or other equipment that have been heated by the passage of electrical current flow. Number 2, current flow through the skin, causing burns by I²R energy. Since these burns occur from the inside out, these burns are almost always third-degree burns. Number 3, thermal or radiation burns are caused by the radiant energy of electrical arc. Number 4, contact with superheated plasma caused by the evaporation of solid materials in the vicinity of electrical arc. The most common injury found in the electrical and computer engineering department is the physical contact with conductors that have been heated by the passage of electrical current flow. Again, resistors will get hot, and if you pass too much current through a resistor, it will catch fire. For some reason, students like to grab resistors that are on fire. If the resistor is on fire, please turn off the power supply, wait for the circuit to cool, then remove the burnt component and replace it with a correct component that will not catch fire. The nervous system contains the electrical pathways that are used to communicate information from one part of the body to another. To communicate, electrical impulses are passed from one nerve to the other. The heart beats when electrical impulse is applied to the muscle that controls it. If some external electrical impulse is applied, the nervous system can become confused. If the current is high enough, damage can be permanent or fatal. The muscular system. The muscular system provides motor control for the human body. When the nervous system stimulates the muscles with electrical impulses, the muscles contract to move the body and perform the physical activity. Skeletal muscles are either flexor muscles, contracts, closes a joint, or extensor muscles, unbends or opens a joint. Electrical shock can affect muscles in at least 3 significant ways. Number 1, reflex action. Muscles contractions are caused by electrical impulses. Normally, these impulses come from the nervous system, but when an externally induced current flows through a muscle, it can cause the muscle to contract, sometimes violently. Number 2, electrical paralysis. Current magnitudes over 10 milliamps may be sufficient to block the nervous system signals to the muscular system. When an external current is flowing through the body, the victim may be unable to let go. This is called an electric hold. Permanent damage. If the current is high enough, the muscle's tissue can be destroyed by burning. Currents of less than 5 amps will cause tissue destruction if it lasts long enough. Because this burning destroys growth areas in tissues, damage can be extremely slow to heal, if at all. The heart. The heart is a fist-sized pump that beats more than 2.5 billion times in an average 75-year lifetime. The atria and ventricles work together, alternately contracting and relaxing to pump blood through your heart. The electrical system of your heart is the source that makes this possible. Normally, a heartbeat starts in the sinus nodes, travels approximately 7 feet per second through the AV node, and right and left bundle branches. The resulting contraction sends blood flowing from the heart. This sequence occurs with every beat. If the path is interrupted for any reason, even a minute or two, changes in the heart rate and rhythm can occur that can be fatal. The pulmonary system. With the exception of the heart, the pulmonary system is the most critical to human life. If breathing stops, which can happen with as little as 30 milliamps, all other functions will cease shortly after. When the lower diaphragm moves down, it creates a partial vacuum in the chest chamber. This in turn draws air into the sacs in the lungs. The oxygen is then passed to the bloodstream through the tiny capillaries. At the same time, carbon dioxide is returned to the air in the lungs. When the lower diaphragm moves up, the air is forced out of the lungs, completing the breathing cycle. Current flow through the midsection of the body can disrupt the nervous system impulses which regulate the breathing function. This disruption can take the form of irregular, sporadic breathing, or, if the current is great enough, the pulmonary system may be paralyzed. When a stoppage occurs, immediate first aid is usually required. Of note, if you are being electrocuted, do you think the current will care that you have stopped breathing and discontinue the current? Again, if you believe somebody is being electrocuted, please proceed to the big red button and depress it quickly, for this will disconnect all power to all stations in the lab. Typical clothing materials. Cotton. Work clothing made from cotton, such as denim and flannel, are a better choice than materials made from synthetic materials. Cotton does not melt into the skin when heated, but rather burns and disintegrates, falling away from the skin. Thick, heavy cotton materials provides a minimal barrier from arc temperatures and ignites quickly. At best, cotton provides only minimal thermal protection. Clothing materials. Synthetic. Untreated synthetic clothing, such as polyester and nylon, provide extremely poor thermal protection and should never be used when working in areas where an electric arc may occur. Synthetic materials have a tendency to melt into the skin when exposed to high temperatures. The melted material forms a thermal seal which retains heat and increases the severity of the burn. Circulation is severely limited or cut off completely under the melted material. This slows healing and the flow of infection-fighting white blood cells and antibodies. The removal of the melted material is extremely painful and may increase the trauma already experienced by the burn victim. Synthetic cotton blends. Synthetic cotton blends, such as polyester cotton, are used to make clothing that is easier to care for. Although slightly less vulnerable to melting than pure polyester, the blends are still extremely vulnerable to the heat of an electric arc. Such blends provide poor thermal protection and should not be used in areas where the hazard of electric arc exists. Chemically treated materials. Both natural and synthetic fibers can be chemically treated to render them flame resistant. While some chemical treatments, such as borax and boric acid salt combinations, may be temporary in nature, others are very satisfactory. Brand name materials offer the best protection for the industrial applications, such as Nomex, PBI, and Kermel. These materials are beyond the budget, range, and time available for this class and should be researched further by those interested in industrial protection clothing. Here, in the Electrical and Computer Engineering Department of UNLV, we are not going to be fashion police. It is up for you to know what environment you're in, what dangers you face, and what clothing you are wearing. Legal safety requirements and standards. The modern trend in electrical safety is toward more and more the individual responsibility, as employees are being held increasingly responsible for their action. Again, employees, students, are being held increasingly responsible for their actions. At the same time, OSHA has become increasingly severe in its enforcement of safety standards. Electrical safety standards and/or requirements are produced by a variety of organizations. Some standards are voluntary, while others are local or federal law. Whether voluntary or mandatory, these standards provide guidance for the proper way to work on or around electrical energy. The Occupational Safety and Health Act of 1970. In 1970, the United States was faced with the following statistics. Job-related accidents accounted for more than 14,000 worker deaths per year. Nearly 2.5 million workers were disabled. 10 times as many person days were lost from job-related disabilities than from strikes. Estimated new cases of occupational diseases totaled 300,000. To address these problems, Congress passed the Occupational Safety and Health Act of 1970. The act created OSHA to continually create, review, and redefine specific standards and practices. The OSHA Act exempts three important categories: self-employed people, farms at which only immediate members of the farm employer's family are employed, working conditions regulated by other federal agencies under other federal statutes. Responsibilities and rights of employees. students. The Act was designed to establish workplace rules and regulations. Employees, students, therefore, are not cited for violations. Employees, students, must read the OSHA poster at a job site, comply with all applicable OSHA standards, follow all employer safety and health rules and regulations, report hazardous conditions to a supervisor, or lab director, or lab manager, report any job-related injury or illness to the employer, again, lab director, lab manager, UNLV employee, promptly seek medical treatment for job-related injuries or illnesses. Employees, students must cooperate with an OSHA compliance officer conducting an inspection if he or she, the officer, inquires about safety or health conditions in your workplace. Exercise their rights underneath the OSHA Act in a responsible manner. Seek safety and health on the job without fear of punishment. Complain to an employer, UNLV employee, the union, or the OSHA, or to any other government agency about job safety and health standards. File safety or health grievances. Participate on a workplace safety and health committee or in a union activities concerning job safety and health. Participate in OSHA inspections, conferences, hearings, or other OSHA-related activities. Accident prevention, investigation, rescue, and first aid. Employee safety behavior. Shown above is an employee safety behavior list as given in the Electrical Safety Handbook. Determine the nature and extent of hazards before starting a job. Each employee, student, should be satisfied that conditions are safe before working on any job or any part of a job or lab. All employees, students, should be thoroughly familiar with and should consistently use the work procedures and safety equipment required for the performance of the job at hand. While working, each employee should consider the effects of each step and do nothing that might endanger themselves or others. Each employee, student, should be thoroughly familiar with emergency procedures. Never administer first aid that you are not qualified to administer. Injuries can be aggravated by improperly administered first aid. Get qualified help quickly. When assessing the victim's condition, learn the ABCs of first aid. A. Check the victim's airway. B. Check the victim's breathing. C. Check the victim's circulation. D. Summon a doctor or medical help. To the right is a table of first aid procedure. Never move the victim unless danger is imminent and the person is in mortal danger. Accident victims should only be moved by trained personnel and only when necessary. Moving a victim who is injured could cause increased problems such as paralysis or even death. Table 7.9 shows a quick list on how to handle unresponsive victims. Even if a person appears normal and states he or she is okay, wait for trained medical help to arrive at the situation. Typical symptoms of electric shock. Victims may lose consciousness. This may occur at the moment of contact, however, it can also occur later. Victims have a weak or irregular pulse. Victim has trouble breathing or has stopped breathing. Small burns may appear at the entry and exit points of electric current. Precautions for performing first aid on an electric shock victim. Do not touch any energized wires with any part of your body or with any conductive tools or equipment. Do not touch a victim who is still in contact with any energized wire with any part of your body or with any conductive tools or equipment. Do not try to move any energized wires unless you are qualified to do so. Qualified in this instant means that you are trained in the performance of such procedures and are able to avoid electrical hazards. After the situation has been dealt with, a report must be filed providing truthful information on the following: an overview of the conditions that caused the accidents, step-by-step description on what actions were taken to help the accident victim, A conclusion with eyewitness reports. Again, after the situation has been dealt with, everyone's statement will be taken. Note, never under any circumstances lie or withhold any information about an accident, regardless of repercussions. Covering up an accident or covering up improper handling of an accident is a serious rule infraction that could result in the failure of the class and possibly have legal disciplinary consequences. We do not cover things up. Our goal is to learn from accidents, both in prevention and treatment. Hopefully, you will take these safety concepts with you in your future employment and labs. Lab safety exam next week. There will be a written lab safety examination at the beginning of next week's lab. You are only responsible for memorizing the material in the red text. The other material is more of a reference. If you do not receive at least 90% on this exam, you will not be able to work in the laboratories. The lab safety exam will be retaken each week until the student has passed the exam. Any previous missed labs must be made up under the supervision of the TA, the lab director, or the lab manager. This concludes our lab safety overview. Again, please take safety to heart to prevent yourself and others from being injured while working in the lab and learning the wonders of electrical and computer engineering.